Assalamualaikum warahmatullahi wabarakatuh. We are from Group 10, representing our group project titled Student Record Search Optimization. And our team member, me, is Najah Amira binti Talmizi. My metric number is 079259.
My name is Nur Izan Izzati binti Muhammad Latif, metric number 079180.
My name is Atifah Merah binti Abdul Kadir. My metric number is 079217.
Okay. This project focuses on a student record system used by university to manage key information such as personal detail, academic result, course registration, disciplinary record, and financial transaction. These records are accessed daily by students, lecturers, and administrative staff for tasks like course enrollment, exam result checking, fee payment, and graduation processing. With the growing student population and increasing complexity of digital system, the amount of stored data has significantly expanded. This leads to slower search operation, especially during peak period like exam session or fee deadline, resulting in delays, miscommunication, and reduced staff efficiency. The problem addressed in this case study is how to ensure fast, reliable, and scalable access to student record. To solve this, the project evaluates the effectiveness of three search algorithms, which is linear search, binary search tree, and hash table hashing. Each algorithm is assessed for its performance in terms of speed, memory usage, and practicality within the context of a real-world university system. So the overall goal is to determine which algorithm offer the best performance and reliability for optimization student record search. So next is summary of analysis finding. In this project, we compare three search algorithms, which is linear search, binary search tree, PST, and hashing hash table, to see which one work best for finding student record in a university system. We look at how fast they are, how much memory they use, and what trade-off come with using each one. So first, linear search is a simple and work well with small or unsorted dataset. It's good when the data keeps changing or when we need to search based on different filters like student status or program. However, it becomes slow when there are a lot of records because it has to check each one with a worst case time complexity of BON. Next is binary search tree. Binary search tree is faster than linear search when the data is sorted and the tree is balanced. It allows us to search by range, like finding students with CGPA above a certain value. The average time complexity is BO log n, but if the tree becomes unbalanced, it can also drop to BON. It also uses more memory because each node stores link to other node. And lastly is hashing, hash table. Hashing is the fastest among all, especially when searching by a unique key like a student ID. It can find data almost instantly with an average time complexity of PO1. It's perfect for big system with a lot of record, but it does not work well for range search or when we want to filter by general attribute. Also, it needs extra memory to handle collision. So overall, hashing is the best choice when we need quick access to specific record in a large system. But depend on the situation, binary search tree is best when sorted data and range query are needed, while linear search is okay for small or flexible search when data change often.
Alright, thank you, Najah. Next, on this slide, we will justify our algorithm selection by comparing hashing, binary search, and linear search based on four key aspects: speed, data requirements, memory usage, and how well they handle updates. We will also relate our justification to the time complexity graph shown below. When it comes to speed, hashing has the fastest performance with a time complexity of big O of n. This means no matter how large the datasets get, the search time stay constant. Binary search is also fast with a big O of log n, which scales efficiently as data grows. In contrast, linear search is slower at big O of n since it may need to scan each item one by one. It's like a sequence. This is reflected in the graph. We can see the blue line, BO of n, BO of 1 for hashing stays flat, while the green curve, BO of log n for binary search grows slowly, and the orange line, BO of n for linear search increase directly with input size. For data requirements, each algorithm works best under certain data conditions. Hashing needs a unique key like a student metric number. Binary search needs data that is already sorted, while linear search, on the other hand, has no special requirement, making it useful in many different situations. In terms of memory, hashing use more memory because of the hash table structure. Binary search and linear search are both lightweight. Next, for handling updates in the data, linear search performs best because it easily adapts to changes without any pre-processing. Hashing also handle update well, but since it doesn't depend on sorted data. However, binary search is less suitable when data changes frequently because the list must be resorted. Looking at the time complexity graph, we see that hashing is optimal for performance regardless of data size, which is the blue one. Binary search scales well, while linear search becomes slower as the dataset grows. Now that we have completed our justification of algorithm selection, let's move on to the next page. Alright, and on this slide, I will explain how we analyze and selected the most suitable algorithm based on our actual use case. We evaluate hashing, binary search, and linear search by looking at their strength, how they work, and how they fit different data conditions in our case study. Each algorithm fits best in different situations. Hashing is ideal for large data sets where we need fast lookup using a unique key, like a metric number. Binary search works best on large but sorted data that doesn't change frequently. Linear search is most suitable for small or unsorted data, especially when we want to filter data based on changing or flexible conditions. Here's how each algorithm works. Hashing uses a hash function to convert a key like a metric number into an index, so it giving us instant access to data. Binary search repeatedly divides the sorted list in half. It will narrowing down the search range quickly. Linear search simply check each item one by one, which is simple but slower for large datasets. In our system, we found specific case study that suits for each algorithm. We use hashing to retrieve a student profile directly using a metric number. It's quick and direct. To find a student name from alphabet, we use binary search because it's efficient if the list stays sorted. We apply linear search when we need to filter students enrolled in computer science and female. This kind of flexible search works best without needing sorted data. Each algorithm has its strength and weakness. Hashing offers extremely fast lookup and scales well, but it's more complex to implement. Binary search is much faster than linear search on sorted data, but it requires that the data stays sorted, which limits flexibility. Linear search is easy to implement and flexible. It's perfect for changing filters, but it's slow for large datasets. So through this analysis, we match each algorithm with a real scenario in our project. Our decision was based not only on speed but also on how well each method fits our data structure and usage pattern. With that, now I will now pass the slide to Atifa for the collaboration tools and final conclusion.
And thank you, Izen. So now to make sure our group work efficiently and responsibly, we use a few useful tools. First, we use the Telegram to communicate. We discuss tasks, share update, and remind each other about deadline. This helps us to stay connected and organized. Second is Google Doc. We use Google Doc to write and edit our report together. Everyone share their idea and we work as a team to complete the writing. The last one is Canva. We use Canva to design our presentation slide. We give feedback to each other and improve the design as a team. This tool help us divide our tasks clearly. Everyone did their part and support either. This show that we work with responsibility and independence throughout the project. Next. So, in conclusion, linear search is the easiest to use. It works well when the data is small or change often. Binary search is the faster, but it only works when the data is sorted. Hashing is the fastest. It gives almost instant result, which is very useful for the big system like university. However, hashing need more memory and must be managed carefully to avoid problem like collision. So, we recommended hashing for large system because it's the more efficient. But linear and binary search are still useful depend on the situation. In the future, research can explore combine this method or using a more advanced index technique to make searching even faster. I think that's all from us. Thank you.